So we're going to start by thinking about opposite operations. What do we mean by opposite operations? Or maybe that's not even the right way of thinking about it. Well, it kind of is, but anyway, like if you perform an operation, how do you undo it, or how do you do other things related to it? So here's an example. If I can do 5 plus 3 equals 8. What are other relationships that are involved in this? So if I'm doing something to the 5, that gives me 8. What would I undo from the 8 to give me 5, right? This is simple. I don't know that you have to write this down. This is kind of elementary stuff. And then another relationship we could just write is 8 minus 5 equals 3. Okay, what in the world are we talking about? Well, we've got this as one possibility. 5 plus 3 equals something. We've got 5 plus something equals 8. Or we've got something plus 3 equals 8. So this is kind of the idea of like doing an opposite operation or undoing an operation. Okay, and this is how you would have learned a little bit about subtraction in elementary school, is what number would you add to 5 to give you 8? Or, in other words, 8 minus 5 is what? Right? So same kind of idea. And we could do this with other operations. So 4 times 6 is what? Or what times 6 gives you 24? Or 4 times what gives you 24? And so the opposite operation here is 24 divided by 6 is 4. 24 divided by 4 is 6. Here's something that's interesting. There is a property called, I think it's interesting, commutative. What does that mean? Commutative means that 4 times 6 is 24 and 6 times 4 is 24, right? It's the same thing if you turn it around. And so 24 divided by 6 or 24 divided by 4 gives you back the same one. Like you can do it both ways work. Make sense? Not all operations are like that. 5 squared is 25, but 2 to the 5 is not the same thing. And taking the square root of something or taking the fifth root of something doesn't give you the same thing. Right? So exponents are not commutative. So it's different. But a lot of these basic operations, they are commutative. Subtraction, not necessarily, unless you turn it around and think of it as addition. But anyway. Okay, so this is like, we know how to do something. 5 plus 3 is 8. Well, how can I, like, what other kinds of things can I do with that? So what's the point of all of this? Well, 5 squared, you know what that means. It means 5 times 5. You know how to do that, right? 25. And then we learn how to do the opposite. So, sort of the opposite. Opposite of what, I guess, is kind of what I'm saying. Sort of the opposite. Or maybe a better way of thinking about it than using the word opposite, might be a bit misleading, is we move the question mark to a different place in this relationship. And what do? Well, we do the square root of 25. Gives me that question mark. Like that's the operation that turns it around to look for that question mark. So the last question mark in this situation is in the exponent. How do I find the exponent? And that's what a logarithm is. Now, in grade 11, this is how you're supposed to do it. 5 to the question mark is, well, I just know this. It's 5 squared. and this is called equating the exponents, and it is something that we will do in this course, okay? And we've actually done this a little bit. I think one of the examples we did with trigonometry looked a little bit like this. So if the bases are the same and they're equal, the exponents must be the same. So I like to write, therefore, the question mark is 2, right? You could solve this. Sounds like it's solving by inspection, kind of, or whatever you want to call it. 2 to the what is 32. So 2 to the something is 2 to the 5. Therefore, the thing we were looking for was 5. 2 to the 5 is 32. But then, of course, they're like what solving by inspection only takes us so far, because then we have ones like this, and we get 6 squared is 36, and 6 cubed is 216. So we start, I guess, guessing and checking, like which one of those, it's going to be somewhere between those two, right? And I don't know, just random guess, maybe something like 2.57 or something like that. Try that on your calculator. See if that 6 to the 2.57. What does that give you? Oh, wow, what a lucky guess, eh? Almost like it was planned. Anyway, so that's not what we're doing. We're not guessing at exponents, but when you know a lot about different powers, you could estimate, but there's got to be a better way. We call it logarithms. So logarithms is how I can rewrite to solve for an exponent. And so what is a logarithm? I mean, it is the operation of figuring out, it is the operation of figuring out what the exponent is. It doesn't have any other simpler notation. We use the word log in it, right? It's not like 6 to the 2. You just kind of write it small and write it above, and it's nice. And logarithms doesn't work that way. So here's the base here's the base of understanding, the foundation of understanding that I was referring to a few minutes ago. Is how do you, because we're doing 1 unit on logarithms, so you've got sort of a week and a half to 2 weeks to really nail this stuff. And it's not too difficult. Your calculator can do a lot of it, but we will have a no calculator test. And you do have to have understanding. So how do you remember really well and drill it into you what the relationship is? And then, in other words, how do you rewrite these? Well, when I look at this statement, what's the base? So that's a power. What's the base of the power? I hear people whispering it's 6. Okay, so the base stays the same when you're working with logarithms. To me, that's the easiest way. Like, force yourself to think about it that way. The base stays the same. And how do we write the base? Log base 6. But then it switches the other parts around. So this is 6 to the 2, my base 6 to the 2, instead of its log base 6 of 36. Equals, and of course, the whole point of all of this is we're looking for the exponent. We're trying to find the exponent. So it has to, the result has to be the exponent, right? Makes sense. So that's how you rewrite it. And then going the other direction, it's easier probably if you're given a log to rewrite it in exponential form, because you can probably kind of figure it out. But again, the base stays the same, right? And the result of a log is the exponent. And the thing you're taking a logarithm of will be your result of an exponent, of a power. So take the time, and the questions that it says, rewrite the following, like take the time and do it and really think about it. And try to get used to, when you first saw exponents, people see things like this. 3 squared, and they want to say it's 6, because you're so used to multiplying. But then you get better and better and better at it, and you start, and then eventually you don't see that as 6 anymore. You know what that means, like it's kind of drilled into you, right? It'll be hard in 2 weeks to get there with logarithms, but you want to get as close as you can, where you understand what a logarithm is and you start to see it for what it is. Any questions about that? So let's rewrite some of these. It's a little bit harder when you have an x in here. Let's rewrite them, and we're going to solve them using sort of the exponential stuff from grade 11, how you should have been doing it in grade 11. And this is one type of question that you will be required to do. Sometimes we do like to do it this way. But then there's other ways that we do it as well, so you'll need to know both, but we'll worry about those other ones after. So the base stays the same. And you know what the answer is. Just put your pencil down and watch. This is what people like to do, but you will not. But this is wrong. This is just bad notation, bad form. Okay, well, 2 to the 3 is 8, so x equals 3. It's not nice form. We don't like it because it's solving by inspection, which really is what we're doing anyway, but it's weird that it doesn't flow properly. The x disappears, and then all of a sudden it reappears. Like it doesn't explain as nicely. And people think, oh, well, come on, that's being so picky. Well, it's picky when it's obvious like this, but if you're solving something bigger, you want to have proper habits of how you can show the flow of work. People's aspirations are not usually to become professional mathematicians who write books. But that is the ultimate aspiration of being good at mathematics. And it's interesting, I don't know if you've ever read about these things, but in the last few years there have been some amazing publications in mathematics, and somebody will write, will discover something new, and they'll write a 200-page book about it that is like one question, and it's a 200-page book that answers the question, right? We think of a question that takes a page as a long question in high school. But anyway, and people take months to read the book and understand it, right? Like, so it's not obvious, even the most brilliant minds in the world, it's not obvious just reading math. And so notation and clarity is important. And this is these are the building blocks of that. Anyway, okay, I talked about that long enough. 2 to the x equals, we do it like this, 2 to the 3, so we're rewriting it in a way where we see the relationship. I've replaced 8 with something that's equal to 8, so we can see that. Okay, and then, as I've always said, I like therefore because it's not clear what operation we did to go from step 2 to step 3, but we're just sort of, it's like we're drawing a conclusion here. And it's not always true with these things that all you have is x. You could have, there are other ones where it would be like 2 to the x minus 5 equals 8. Therefore, x minus 5 will equal 3, and you'll continue to solve, right? So there are different kinds of questions like this. Okay, go ahead and try B. Today is really about rewriting logs and starting to think about what they are and what they do, but we're not really solving with logs yet. But we're thinking about the relationship they have with powers, and we're going to do a little bit of graphing. So 3 to the x equals 3 squared, therefore x equals 2. And some nice review of some different properties of powers that we haven't seen a lot of in this course. So you would always start a question like this by rewriting it. And then if you think about the other examples that we've done, the next step looks like this. 4 to the x equals 4 to the something. I got to fill in that box. So what can I raise 4 to the power of to make it 1 over 400? Negative 1. We haven't seen a lot of that in this course. Negative exponents make something a fraction. Does not make the thing a negative, right? Ooh. Don't make that mistake. Therefore, x equals -1. Okay, very nice. There are two common bases that we use with logarithms. So if you have a more simple calculator, as long as it has a log button on it, when you do log of something, you could try it after we've solved this one, you could try it on 100 log of 100 or 100 log and see if it gives you the same answer that we're going to get right here. Because your calculator probably automatically does things in base 10. That's a common base that we use in technology with computers, that sort of thing, with logarithms. Base 10. I've seen computer programs that use the other one, though, which is a number that you may have heard of but wouldn't really have used very much, E. There's a number called E. You know, like we have a number called pi and a number called I and a thing. So there's a number called E, and E is the natural logarithm, and it has another name called ln a little bit. And so sometimes you might see log base E, and if you take calculus, you'll see that. Okay, but base 10 is probably what your calculator does. So let's solve this. So 10 to the x equals 100. 10 to the x equals 10 squared. Therefore, x equals 2. So if you do log of 100 equals on your calculator, do you get 2? Alex, what were you going to ask or say? What were you going to say? You had your hand up. Oh, okay, never mind. Sorry. I thought you did. So try that on your calculator, see if it gives you 2, and it should for most of you, I think. And so you know that your calculator is working in base 10. So it'll only work for that. Now, newer calculators might have an extra button where you can put in the base. That does make it easier, but we're going to learn some ways that you wouldn't need that anyway. And with a no calculator test, you wouldn't be able to use that anyway. So it wouldn't matter, right? So we still need to understand this stuff. Log base 10 of -100. Try that one on your calculator. Before we solve it, let's try that on our calculator. This is going to take away our opportunity to think maybe we should have tried it first. What'd you get? Error. Doesn't work. So 10 to the x equals -100. What exponent can I raise 10 to that's going to give me a negative? There isn't one, right? So looking at it like that, that makes sense. Not possible. That will become important later on because sometimes that pops up in certain situations. But that's something to think about. So the thing I'm taking the log of can't be negative. Could the base be negative? Alex? Does it depend? Yeah, good. What do you mean by that? Kinda, right? So I think your calculator probably won't know what to do with the negative base, but that doesn't mean it's impossible. As always, rarely these things are impossible. They're just not possible with what we have learned so far. So there's other ideas where you could start to explore negatives, but for us, pretty much, you don't want to see negative bases or negative things you're taking logs of. Okay, last one here. So again, I got to rewrite these with the same base. And what could I raise 1/3 to? That's going to give me 9. Very nice. -2, because 3 squared is 9, and it's going to give you the reciprocal when you make it a negative. Try it on your calculator if you're not sure. This is something you've seen in grade 11, and so hopefully it'll come flooding back to you as you work with it. Any questions about that so far? Okay, moving on. What is the inverse of y equals 2 to the x? What is an inverse function? Who remembers that? We did that in this course. You do that in grade 11 as well? How do you find an inverse function? That was a long time ago that we did this.
Just switch to x and y.
Very nice. Switch the x and y. So if I do x equals 2 to the y, And then how do I rewrite that? Keep the base the same. Log base 2 of x gives me the exponent. There's the inverse. So we interchange x and y. That's how we get the inverse of a function. What else do we know about inverse functions? Like, remember what you do in grade 11 and what we did earlier? We found them, but we also graphed them. And so what about the graph of an inverse? This is a good review for the exam, right? Yes, you exchange the points, you interchange the points x and y. So if it's 0, 2, it becomes 2, 0. Very nice. What else? Anything else? Okay, well, let's take a look. Remember, it's a reflection and the line y equals x, right? So it should look like a reflection. So when in doubt, if you are graphing a log function, you could think about it as the inverse of an exponential function. So y equals 2 to the x. Careful of the scale here. I'm counting by 0.5s. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16, and so on. We know exponential growth is fast. Okay. 2 to the negative 1 is a half. 2 to the negative 2 is a quarter. 2 to the negative 3 is an eighth. 2 to the negative 4 is a 16th. So I can use this to graph the inverse and see what a logarithm function looks like. 0, 2 becomes 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. 2, 4 becomes 4, 2. Negative 1.5 becomes a half and negative 1. Easy enough? So it looks like a reflection. You can see that it is, but interchanging the x and y is a nice way of thinking about it, at least for now. Okay, one more. You can just watch. I don't know that you have to actually really copy this down right now. So 1/3 and its inverse. So this is like, the way I think about this is it's just a reflection in the y-axis, because it's kind of like 3 to the x, except negative values give me the flipped, and positive values give me the flipped results. So 1/3 to the 0 is still 1. But 1/3 to the positive 1 is a third. 1/3 to the negative 1 is 3. So 1, 2, 3. And then the next one's going to be off the graph 9. And then they're going to get small really fast. Okay, and then the inverse is going to be, this is something that looks very different from the last pair of functions, where let's see. So 0, 1 becomes 1, 0. That one's still fine. And then this is -1 and 3 becomes 1, 2, 3, -1. And then we've got this and this and this. So it looks like this. Like in some ways they almost look similar. But their asymptotes are quite different. Like there are things that are certainly quite different about them. Any questions about that? There's your homework. We're going to do more graphing of this next week. Here's if we want to zoom out a little bit, sort of see what they look like. So that one I think is fairly straightforward. There's the two. So see the purple one has an asymptote on the y-axis, and the red one, or the orange one, has an asymptote on the x-axis. And what the orange one is doing this direction, the purple one is kind of doing that direction, right? So there are certainly similarities. Any questions about any of that? So rewriting them from, so not complicated stuff today, but important base of understanding, I think.